Okay, in this podcast we're going to talk about pressure from a gas. So as you know, air around us is made up of molecules. It's actually a mixture. The blue is probably nitrogen, the red oxygen, two primary components, but it's got small amounts of other gases. But it's all over the place. It's all around us. Here's a picture of the governor, and you can see all around him are molecules. Too small to see individual ones. But even though they're too small to see, they do have mass. So like all matter, one of the definitions of matter is it takes up space and has mass. So air molecules do have mass. And atmospheric pressure is gravity pulling down on these air molecules above us from the atmosphere, pulling towards Earth. And it's actually a tremendous force that these molecules get pulled down on. It's 14.7 pounds per square inch, or PSIs, which doesn't sound like too much, but if you think about it in terms of a square foot, it'd be a ton. So if you were to lay on your stomach, let's say, and imagine making a square by square on your back and having a ton of pressure come down on it, that's a tremendous amount of pressure. So the question is, why aren't we squeezed by this or crushed by this tremendous force? And the answer is that the pressure is equal in all directions. The equalization makes us not feel it. But it is very strong. And here I'm going to show you in a video on the highway. Sometimes it's pulled by a train, it can be pulled by a truck. And let's take a look what happens to it when it sits out in the dock overnight. Well, look at that. Just absolutely crushed. Here's another one coming up that we will see a similar thing happening to. And this is actually a staged one, and you can see the crush. Okay. So let's talk about what happened there. Alright, so if you imagine these tank cars come in and they have liquid in them, and those liquid gets delivered, and then they come back dirty, and they have to be cleaned. So the way they are cleaned is there's a vent that gets open, and then the worker will spray high pressure hot water into the container, wash down the sides, and then the material will cool. But what happened in this case was the operator did not close the valve where he should have kept it open. So what happened is you have this large volume of steam in here, and when it cooled, that steam condensed into just a couple drops of water, and you had all that space where there was no gas molecules. And what causes pressure inside a closed container is gas molecules hitting the sides of the container. Because there wasn't any gas, there was a vacuum in here. So because there's no pressure pushing up from the molecules, the atmospheric pressure was able to achieve this absolute crush of this huge tank car. That's the force of the atmospheric pressure pushing down on that tank car. Pretty amazing. Okay, so let's take a look now. Okay, so if you can think about atmospheric pressure as a column of air above you. So the higher you are up, the smaller that column is. So if you get this little guy up here, you get a pretty small column of air above you, so it's going to be relatively low pressure. As opposed to if you were down here, you're going to have a much larger column of air above you, pushing down on you, causing higher pressure. So the higher the altitude, the lower the pressure. So you're going to have a lot more pressure at the bottom of a pool than you will on top of a mountain. And here's a chart that shows this. And you should pause along the way and take notes in your note packet. But the higher the altitude, the lower the pressure, right? If you come down in altitude, you're going to have higher pressure. So as elevation goes up, the barometric pressure goes down. The tool we use to measure air pressure is a barometer, and it's used to help us indicate what's going to happen with the weather. So let's talk a little bit about how the barometer works. This is something you need to know for the test. It was actually developed by a guy named Evangelista Torricelli, an Italian scientist, And the way it works is you have this open pool of mercury that the atmosphere can push down on. And that mercury then goes up a tube, and the height of that mercury in the tube is an indication of the pressure from the atmosphere. Okay, so this weight of the mercury is also pushing down on the pool, so it's sort of this tug of war, and depending on how high this goes, it's an indication of how much pressure there is. So let's take a look at a little animation on how the barometer works. So here's the barometer. We've got our pool of mercury. We've got our the pressure from the air is pushing down on that pool of mercury, and then you've got mercury able to rise in this column. So if I hit it to go, the pressure of the atmosphere is pushing down, causing the height of the mercury to rise. There is pressure pushing down on here, so when it's equal, it stops. And then you can read the height of this mercury column, and normally it's in millimeters of mercury, but it could also be inches or centimeters of mercury. But a typical unit of pressure is millimeters of mercury, which is what is shown here. So we can measure atmospheric pressure, and if we take the same barometer to the top of the mountain or the bottom of the hill, the pressure is going to be lower at the top and higher in the valley. Barometric pressure is used to tell us what's going to happen with the weather. So if the barometer is rising, that means we have high pressure coming in, and that usually means we're going to have beautiful, sunny, clear weather. But a falling barometer means the air pressure is decreasing, and that means a storm is probably coming. So behavior of a gas depends heavily on temperature and pressure. Unlike a solid, where the volume will stay the same in different temperatures and pressures, a gas, if I put pressure on it or if I heat it up, it's going to really change its other properties. So when we're talking about things like volume of a gas, it's convenient to talk about what conditions they're in, and we often talk about standard conditions, specifically standard temperature and pressure. Standard temperature is defined as 0 degrees Celsius, which is also 273 degrees Kelvin. It's also 32 degrees Fahrenheit. And standard pressure can be expressed in many different units, including these most common ones: 1 atmosphere, 760 millimeters of mercury. The actual standard, scientific standard, is 101.3 kilopascals. In the U.S., we use PSI, or pounds per square inch. So here's all the different units of pressure, and these are what they are at STP. So we can take a problem, and we can say, let's take a look at how many atmospheres are in 55.1 kPa. And if we did that, we can set up a factor label, right? We know, let's pause this for a second. Okay, so we can say we have 55.1 kPa. And what I know is for STP, 101 kPa, 101.3 kPa is standard pressure, and I also know that 1.0 atm is standard pressure. Using my factor label, I'm able to calculate that 0.544 atm is my answer. Okay, on page 7 there's a little bit more complicated problem. It's asking, it says the barometric pressure at the Philadelphia airport is 29.58 inches of mercury. Of course, in the U.S. we use non-standard units, and we actually are measuring inches of mercury in the barometer. The question is, how many ATMs is this? So what I know is 1 ATM is 760 millimeters of mercury, but this is inches. I know 1 inch is 2.5 centimeters, and 1 centimeter is 10 millimeters. So we can do a whole factor label here. My given is 29.58 inches, and what I know is 1 inch is 2.54 centimeters, and what I know is 1 centimeters is 10 millimeters, and what I know here is 760 millimeters of mercury is 1 atm. Okay, remember I set my factors up so that I can cancel out units, inches, centimeters, millimeters, and I'm left with atm. And if I plug and I chug, I end up with 0.9886 atm. Same number of sig figs as my given. Okay, and that's going to do it.